Alrighty, so now we're going to look at a sampling distribution for a sample mean. So now instead of looking at the proportion of the population that contains this specific characteristic, we're going to look at the averages of the population, or the population means. And so our parameter now, instead of capital P, is going to be the Greek letter mu, which represents the population mean. And the statistic that we'll use to estimate mu is going to be x bar, the sample mean, because this is an unbiased estimator of the population mean. Now, in order to find the sample average, you'll take the sum of the observations in the sample, and it could be IQ, it could be weight, it could be scores, etc., and you'll divide that by the sample size. And this is the idea that if we were to give everyone a piece of the pie, this is how much everyone's sliver would be worth. And so this is dealt with for quantitative data. So very similar to a population proportion, we see here that in our population, and again, could be people, could be objects, could be nature, who knows, there exist these two parameters, the population mean, mu, and the population standard deviation, sigma. So that is the truth. Those are the true values. That's the population. That's everyone. That is a target of interest, and that is the true value, the parameter. Well, I'm going to continue to take SRSs of size n, and from each random sample that I'm taking, I'm going to get a sample mean. And if I were to take all possible sample means, they would be clustered around the population mean, and they would follow a spread dealt with this formula, or the standard deviation of the sampling distribution of x bar. So again, here's my truth, here's what I'm using to estimate, and here are all of my estimates in order to capture the truth. Now, again, like I said, the conditions are not going to change much for us. So again, I need them to be stated random, and this could be through a random sample or random assignment. And you'll notice that we haven't done too much with experiments. That's going to come more in handy when we start dealing with inference procedures. For now, though, we're really going to focus on random samples. Next up, we want to verify that there's independence within the sample, and we'll do that by checking the 10% condition if we're sampling without replacement. Again, just saying that our sample size is no more than 10% of the population size. And then lastly, we have to check that the shape of our sampling distribution is approximately normal, and either the initial population is normal, or we can use the central limit theorem, which says as long as our sample size is greater than or equal to 30, then we'll have an approximately normal sampling distribution. And these will come to me from the AP Stats formula sheet. If I'm looking at one population, here's my mean. Here is my standard deviation, again, of the sampling distribution. Notice that mu and sigma, those are going to be of the population, but mu of x bar and sigma of x bar are going to be relative to the sampling distribution. And I did not stamp that in the earlier videos there with 5.1 and 5.2, so my bad. But again, we see that our sample mean is distributed normally. It's got a mean of this and a sigma of this. And notice that if it's got x bar, that's about the sample or the sampling distribution. And if it's just got an x, I did that as our population. So suppose that particular moths can infest avocado trees and potentially damage the avocado fruit. A farmer plans to investigate the number of damaged avocado fruit on moth-infested avocado trees of a certain variety. And a recent article states that the population distribution of the number of damaged avocado fruit on moth-infested avocado trees of this variety is symmetric with mean 6.1 and standard deviation 1.8. And notice it didn't say it was normal, it just said it was symmetric. So it could be bimodal, it could be unimodal, it could be uniform. We just know that it is symmetric with those two parameters. Now we are asked to describe the sampling distribution of the sample mean for random samples of 36 moth-infested avocado trees of this variety from the population. So again, if I were to take all of possible samples of size 36, and I would take the mean from each of those samples and plot those means, I would get this theoretical sampling distribution. Well, our first condition is met because we're taking random samples of 36 trees. Our next condition is that it is reasonable to assume there's at least 360 avocado trees of this variety in the population. And notice that I wrote it a little bit weird here, so instead of writing out a sentence, I wrote it out symbolically, and this is totally allowed on the AP exam as long as it is in context. So my sample of 36 trees is less than or equal to 10% of all avocado trees of this variety. That's the same thing as saying there are at least 360 trees in the population. Now, the normal model here will be appropriate. We weren't told that it was normal, but I was told that my sample size is 36. So the normal model is appropriate by the central limit theorem since 36 is greater than or equal to 30. So again, I'm addressing how each condition is met. I'm not just putting random check mark, independent check mark. I'm saying a random sample of. independent by 10%. The normal model is appropriate since, it meets these criteria. Well, now I'm going to use my original population parameters, and I'm going to compute the parameters of my sampling distribution, again, just using basic substitution. And I'll get that my sample average is distributed normally with a mean of 6.1 and a spread of 0.3. Well, from here, now I want to find the probability that the sample is to contain between 5.3 and 6.2 damaged avocado fruits. So again, we start off by writing our probability statement. We convert these to z-scores. We find the probability between the two observations, and if we were to plot this on a normal curve, it would look something like this, hopefully a little bit more symmetric. And we'd get that there's about a 62.55% chance that the sample of 36 trees is likely to contain between 5.3 and 6.2 damaged avocado fruits. So again, once we verify the conditions and we construct the sampling distribution, we just treat these problems like a normal model. So what I want for you all to do now is go ahead and take a look here. Sampling distribution questions tend to show up mostly in the multiple choice section. So I'll just let you guys practice. So go ahead and pause the video, look at example 2, 3, and 4 in your notes, give yourself some time, and then we'll come back and review together. Alrighty, so that time will start now. So one very infamous problem from the AP exam is constructing the sampling distribution. And again, you're using textual evidence. Doesn't matter what the initial population is, because as long as our sample size is sufficiently large, we can use a normal model. So we're taking all possible simple random samples of size 100. We are taking, our sample size is 100, and so hopefully there's at least 1,000 homes in the sample size, and guess what? There's over 5,000 homes, so we meet that condition. And then lastly, even though our population was initially skewed to the right, the large sample size ensures that the sampling distribution will be approximately normal. So just go ahead and use my formulas, do some substitution, and find the value. And I'll get that my sample mean is distributed normally, with a mean of $206,274 and a standard deviation of $3,788.10. So again, just using verifying conditions, using formulas, giving the distribution. Now, this one is one of my favorite problems, and I'm actually, you know what? I'm just going to give you the answer, and you will be responsible for figuring out how we got there. So here's the answer for this question here. And we'll look down here as well for another question for you. And here we go. So the last thing, that's going to wrap up the lesson, just quick and easy, but the last thing I want to ensure is that when we use the central limit theorem, the means or the unbiased estimators are closely approximating those population parameters. P hat estimates P, X bar estimates mu, S estimates sigma. Now, the more and more samples we take, we notice that there tends to be less variability, again, because of the law of large numbers. Taking more and more samples, we're going to get closer and closer to the truth. So that kind of explains this question here. Why is it that B has the largest number of samples? Because those samples are going to start to take on some of the same values. So the more and more samples you take, the narrower your distribution, the less variability there is. Now, the fewer samples you take, there's going to be more variability because each one of those has a higher impact on that initial distribution. So that's the idea there. Other than that, we are basically almost done with our sampling distribution. And again, I'm finding all of these formulas just from the back of my AP Stats formula sheet. It's helpful for me because it keeps all the formulas organized. I just have to recognize, am I looking at categorical or quantitative? Am I looking at one population or two populations? And from there, it's just a matter of subbing into the formulas and verifying your 3 sins of statistics. But that wraps up about 80% of the unit. Now, in the next lesson, we're going to look at the sampling distribution for the difference of means. So stay tuned for 2 sample inference for quantitative data.